Okay, guys, this is our fourth session of our video lectures on Basic Physics 2, Electricity and Magnetisms. And last time, actually, we stopped after we defined the capacitance. Today, we are going to continue the discussion of capacitance and move forward. I'm going to, after I remind you what we had at the last time, then we are going to discuss how we can discharge and charge a capacitance, what happens when we are charging or discharging it, and then we are going to see how we can connect the capacitors if we have more than one, let's say 2, 3, 4, and so on. And after that, actually, we are going to close the discussion of the capacitance, and in this video, we move to another subject. We will discuss the electric current, the resistance of the materials against the electric currents, and also we are going to see some electric circuits. But first, let me remind you what we had at the last time. We defined the capacitance as a relation, linear relation between the charges in the capacitor and the electric potential. Such that Q, the electric charge accumulated in the capacitor, can be written through a linear relation in terms of the electric potential between the plates, and if we introduce the capacitance in this relation. And the capacitance of a capacitor, remember, purely depends on the geometry of the capacitor. So if we have a parallel plate capacitor, let's say sigma is the surface charge density of the capacitor. So this is parallel plate capacitor, and we find the capacitance of such a capacitor is simply equal to epsilon 0 A over D. Epsilon 0 is the permittivity of the empty space, A is the area of the plates, and D is the separation of the plates. But we define also other types of capacitors, like the cylindrical capacitors. If I have two coaxial cylinders length L, one has a radius A and the other has a radius B, then I can write this is cylindrical capacitors, and we find their capacitance can be written like 2 pi epsilon 0 L over natural logarithm of B over A. And B is the radius of the outer cylinder, and A is the one of the inner cylinder. And the last type actually we define is the spherical capacitors. In this case we have two concentral spherical shells. One has a radius A and the other has a radius B. This is spherical capacitors, and also we calculated their capacitance, and we found that it's going to be 4 pi epsilon 0 A times B over B minus A. So A and B are again radii of the spherical shells. A is the one of the inner sphere and B is the radius of the outer spheres, and its capacitance is 4 pi epsilon 0 A times B over B minus A. And see, the capacitance for all types of capacitors like parallel plates, cylindrical or spherical capacitors is purely based on their geometry. This is for parallel plates, this is for cylindrical, and this is for spherical. Let's take a close look to the spherical capacitors. So if I ask you what happens if you charge only a single sphere, isolated sphere, let's see how we can answer this question by taking it from here. So let me make some space here. I'm going to keep the spherical one at the bottom. So this equation implies that if we charge a single spherical shell. All right, we have only this one. Let's say its radius is A. And what is the capacitance of this single spherical shell if I charge you? And how we can get the answer by using this one? Actually, if we have as an isolated spherical shell, it means the second shell, whose radius is B, is at the infinity. Okay. If I put an outer sphere at the infinity. What I mean, when I put another sphere at the infinity, it means its radius B goes to infinity. So I'll take the same equation here, but I take B to the infinity. All right, let's play with the equation. So the capacitance of such a capacitor can be written C 4 pi epsilon 0 A times B over B minus A. If I rewrite this equation by using a simple mathematical trick, 4 pi epsilon 0 A times B over, if I put the denominator in the common parenthesis of B, 1 minus A over B. And I can cancel two b's here, so I'll find 4 pi epsilon 0 A over 1 minus A over B. Okay, now let's take the step here. What happens if I take B goes to infinity? It means A over B goes to 0. And then when A over goes to 0, I'll take this capacitance will be equal to 4 pi epsilon 0 times A, which gives you the capacitance of a single isolated spherical shell, of course. All right, so let me remind you that the energy stored in the capacitor over this discussion. So you want to charge this spherical shell, so you need to spare some energy, some energy. And how much energy do you need to put some charge Q on this spherical shell? Let me write it down. How much energy is required to charge an isolated spherical shell? And let me remind you that the energy used stored in a capacitor, which we calculated as 1/2 Q times the electric potential. And this Q is the charge we put on the spherical shell. But also we know from the linear relation between the charge and the electric potential, I can write C times V. So if I put it here, the energy can be written 1/2 C V squared. So, and what is the electric potential for a spherical shell? Actually, you need to go back and remind yourself what is the electric potential on the surface. Actually, we calculated the electric field and electric potential on the surface of this spherical shell, and we found that V is equal for such a spherical shell is K total charge of it over A. A is the radius of the shell, and you can plug all these things to calculate the energy, electric energy you need to spare to charge this sphere. This is also equal how much energy you stored in this capacitor. Okay, so this is a little bit refreshment and also show you some interesting facts about the capacitors. Now, Remember how we started the discussion of capacitance? In the beginning, we had a charge capacitor, like a sigma and minus sigma, the charge, the surface charge density of the plates. And I told you what happens when I connect these two plates. All right. When I connect two plates, actually the charges over a surface, over a plate, will start moving to the other plate. Okay. So they will start moving from this plate to another one. Actually, we know the negative charges are moving because electron, the negative charge carrier, is much lighter than the proton, positive charge carrier. But conventionally, we assume the positive charges are moving. So the positive charges will start moving from this plate to the other plate. Until when the charges move from one plate to another, until the plates become neutral. So when I connect two plates, the charges will start moving from one plate to another one, and at some point that motion of the charges should stop. And when it is going to stop? When the plates become neutral. When the plates are neutralized, then there is no electric charge move from here to here. All right. Actually, we are going to visit this discussion again in more details, but so far this is enough. And we call this process, discharging. Okay, this process is called discharging. Discharging a capacitor. Okay, if you put some device here, actually while the charges are moving, they also run the device. So if you put a bulb here, then you will see some lights. If you put a heater here, you will feel some heating from here. Or if you put your phone here, the charges will run your phone so you can use it, and then at the end they're going to come to the other plates, and the charges stop when all plates becomes neutral, so your device will stop running. Alright, this is the discharging, and discharging actually lasts till all plates becomes neutral. What if I have you, I give you an empty capacitor. Okay, this is an empty capacitor, and I'm asking you how we can charge it. Okay, to charge it, actually it is quite simple, because you are charging your capacitors you are using every day. For instance, the battery of your phones. Actually, you are discharging the battery of your phones every day, and then you are charging it to use your phone. How you are charging? Actually, let's say this is the battery of your phone, then you are plugging it in to a switch. So what is that switch? That switch is actually a power supply with a potential difference, electric potential V. This is C, and let's say the electric potential of this capacitor of your battery is Vc. When the capacitor is empty, see, then Vc is equal 0. Vc is the electric potential difference between two plates, but no electric charge yet in the capacitor stored, so the electric potential difference between two plates is equal 0. So when I plug it on and then to the power supply, that power supply starts moving some charges. Okay, let's say in this direction, some charges. But the point is, we have an empty capacitor, we just plug it in the power supply. Why the electric charges are moving? Because this power supply is generating a electric potential difference between these two plates. Okay, and the electric potential difference, just remember, when you have an electric potential difference, you can relate it to the electric fields, like E times D, for instance. D is the separation of these two plates. So that electric field, actually, remember how we define this electric field? E is equal the electric force over the charges. So actually the existence of electric field means the existence of electric force, and this electric force actually moves the charges from power supply to the battery. But so this process is called charging. Now when you connect your battery or your capacitor to a power supply, then you start the charging process, and this charging process should stop at some point, right? When you charge your phone, actually after some time you see that your battery of your phone is full, like 100% full. So the charging should stop. When the charging is stopped, the electric potential of the power supply and the electric potential of the capacitor will be equal to each other. So charging of, let's say, a capacitor, charging of a capacitor continues until we see equal V. So when we see the electric potential difference between plates and the electric potential power supply is equal to each other, then all this system has the same electric potential, right? V is here, so the electric potential difference here and here becomes zero. When it is zero, the electric field will be zero. When electric field is zero, the electric force will be zero. So zero force will move no charges. So the charge motion from the power supply to the capacitor will stop when the electric potentials of capacitor and the power supply becomes equal. So before moving, let's take a close look to our notation. As you see, this is the power supply. And when I put the power supply, I put one side longer than the other side. So what does it mean? The longer side of the power supply, shows the positively charged side, shows the positively charged side. And as you can guess, the shorter side is negatively charged. So in this case, when I give you a power supply, actually I don't have to tell you which side is positive, which side is negative. You need to just check how it is put into the system. So the longer side will be positively charged and the shorter side will be negatively charged. And again, just keep in mind, negative charges actually are moving, but conventionally we assume the positive charges are moving. So the direction of the charges will be chosen from positive side to the negative side. Okay, so after that point, I don't have to tell you the direction of the charges, the motion of charges, and also I don't have to tell you which side is positive and which side is negative. You need to check the power supply in the system, in the figure, and when you see the longer side, it's going to be the positively charged, and when you see the shorter side, it represents the negatively charged side. Okay, so this will be our notation. But now, this is charging, and we discussed discharging. So what happens if you have capacitors more than one? Let's say 2, 3, 4, 5, and so on. So you can connect the capacitors in different ways, right? If you have capacitors more than one, then I can connect them into the same system in different ways. One way is the serial connection. Let me write with red. Okay. Serial connection means actually when you connect two capacitors So we can generalize this discussion to more one, but I keep it simple, so I'll have two capacitors in the beginning. Let's say this is C1 and C2. When I connect them to a power supply, this V, so again the charge will move from the positive side and pass through C1 first and then C2 and then comes back to the power supply again. So it's going to charge these two capacitors together, right? And when it is going to stop, after we charge these two capacitors, it has the electric potential V1 and it has the electric potential V2. And when it is going, when the charging is stopping, when V, the electric potential of power supply, will be equal V1 plus V2, then it stops. The charging will stop. All right. If I send the total Q amount, if I send a total amount of charge Q from this power supply, that Q comes to the C1 first. So at the end, its total charge will be Q, and then it keeps going and it arrives at C2 the same amount of charge, because there is no other way. This charge should move all the way, so the same charge will come to the second capacitor and then comes back to the power supply. So at the end, actually the total charge in both capacitors will be equal Q. So from here, Q will be equal C1 times V1, remember the relation between the total charge and the electric potential, and from the second capacitor the same Q will be equal C2 times V2, and it's going to stop when V1 plus V2 is equal to the V of the power supply. So now we have two capacitors, but actually I want to have only a single capacitor which makes the same work of this system. So if we want to reduce the number of the capacitors into one, and if I connect it to the same power supply, but these two capacitors will store some energies, right, in terms of Q and electric potential, or capacitances and the electric potentials. But I want to store the same energy from the same power supply with the same amount of the charge into a single capacitor. So I need to construct this system, but these two systems will be equal to each other. So I call it like C equivalent, the equivalent capacitor. So how much capacitance I need to have in this system to store the same amount of energy without changing anything, with the same amount of Q and from the same power supply. So again, the Q amount of charge will start moving here, come to the equivalent capacitor and back to the power supply. So when it is going to stop, remember we see the electric potential between the plates equal V, then the charging will stop, and from this system I can write V will be equal so that the same charge Q times C equivalent. Okay, but how I can calculate it? Assume that you know what is C1, what is C2, but you don't know what is C equivalent. So how we can calculate the equivalent capacitance in terms of the C1 and C2? Okay, let me just make myself a little bit space. I'm going to redraw these figures, but smaller this time. So we have this in the beginning. But this is C1, C2, V1, V2, and the Q is passing through the all capacitors. But I want to have this one, C equivalent. It's going to be V and V again, but with the same amount of the electric charges. So from here, let me remind you what equations we have. Now Q is equal C1 times V1, the same Q will be equal C2 times V2, and from here the same Q will be equal C equivalent times V. And we have from here V is equal V1 plus V2. Okay, we are going to go with this equation to calculate the equivalent capacitance in terms of C1 and C2. So let's write here. I'm going to rewrite all this equation, but for the electric potential. So by using this equation, I can write V is equal Q over C equivalent. All right. By using this equation, I can write V1 will be equal Q over C1, and this equation I can write V2 will be equal Q over C2. Now let's get back to this equation. V is equal V1 plus V2, but if I plug all these equations into here, Q over C equivalent will be equal V1 is here, Q over C1 plus V2 is here, Q over C2. If I cancel all Q's from the terms, then I can write 1 over C equivalent will be equal 1 over C1 plus 1 over C2. So actually, if you know what is C1 and C2, you can easily construct such a system with a single capacitor, and its capacitance can be calculated by following this equation. So in this example, we have only two capacitors. What happens if we put more capacitors into the system? Actually, it is quite easy to generalize. If we have n capacitors serially connected, like here, if we have like this, and this, they are connected to a power supply. Let's call it C1, C2, C3, and Cn. But I want to construct I want to store the same energy, or the summation of the whole energy of these capacitors into a single capacitor without changing anything, like total charge Q, C equivalent. Actually, it's quite easy to generalize. 1 over C equivalent now will be equal 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over Cn. So you need to just sum all the inverse of all the capacitors here, which is going to be equal to the inverse of the equivalent capacitor. So equivalent capacitance in serial connection of capacitors. Alright, when you connect the capacitors serially, then the equivalent capacitance will be equal the summation of the inverse of all capacitors, and it will give you the inverse of the equivalent capacitor. So you need to just inverse it after you calculate. A second way to connect two or more capacitors are the parallel connection, right? You don't have to connect them serially, right? Okay. Alright. Now parallel connection of capacitors. Now again, let's start with the two capacitors, and if I connect them to a power supply parallelly, like this, and this is our power supply. Let's call it, this is C1, this is C2, and this is V. Now, if I say, I'm in the same discussion, the charges will start moving from this side, but it's going to be split here at this point because there are two ways. So if total charge is Q, I send from this power supply, at this point it's going to be like Q1 here, and the rest of the charges will keep moving through C1, or let's call it like Q1 here and Q2. So actually now the total charge of the capacitors will not be equal to each other, right? Q1 doesn't have to be equal Q2, but from the electric charge conservation, we know the total charge here should be equal to the total charge I take off from the power supply. So from here I can write Q is equal Q1 plus Q2, but in general Q1 is not equal Q2. In the parallel connection, actually the charging will stop when this both sides, I mean all sections will have the same electric potential of the power supply. So it's going to stop when C2 has the electric potential V, and simultaneously when C1 has the electric potential V. Alright, so I can write again like Q1 is equal C1 times V from here, and Q2 also will be equal C2 times V. And in general, if C1 is not equal to C2, Q1 is not equal to Q2 again. Now, the logic is the same. These two capacitors will store some energy inside themselves. So I want to have the same energy, I want to store the same energy with the same amount of Q into a single capacitor. So when I construct this system with a single capacitor, so C equivalent V, and I want to send the same amount of the charge, and again when it is going to stop, when the electric potential of this capacitor will equal to V, then the charging will stop. So now let's assume that we know what is C1 and C2, but we need to calculate C equivalent like we did in this serial connection, but now we have parallel connection, and from here I can write total charge Q is equal C equivalent times the electric potential, and its electric potential will be equal to the electric potential of power supply. So in this case, in the case of parallel connection, how we can calculate the C equivalence? Let me make myself some space. I'm going to redraw these systems smaller. Alright, in the beginning we have this. V, C2, C1, their potential will be V and total charge Q, but at this point Q2 follows this way while Q1 follows this way. And now I want to construct another system with a single capacitor, and that capacitor will store the same amount of energy I can have in this system. So V will be here and Q will be the charge. From here, what I have, from here Q1 is equal C1 times V, Q2 is equal C2 times V, and Q is equal Q1 plus Q2. From here, I also have Q is equal C equivalent times V. Now, we are going to move with this equation. Q will be equal Q1 plus Q2, which is required by the electric charge conservation. Okay, we are going to see this electric charge conservation later after we discuss the electric current. All right, now Q is equal Q1 plus Q2. So let's write the Q. Let's plug all these three equations into here. Q, from this equation, I can write C equivalent times the electric potential will be equal Q1 plus Q2. Q1 can be written by using this equation. C1 times V plus Q2 can be written by using this equation as C2 times the electric potential. And if I put them in the common parentheses of the electric potential, I can cancel this too. So C equivalent will be equal simply the summation of the capacitances of the capacitors. So in the case of parallel connections, if you connect two capacitors parallel to each other, the equivalent capacitor will be simply the summation of the capacitances of the capacitor. So C equivalent will be equal C1 plus C2, and it is easy to generalize it. What happens if we have three or more capacitors in the parallel connection? Just let us finalize this discussion with the generalization of this C equivalent relation. If I have such a system, so C1, C2, C3, and many other capacitors and Cn. If I connect n capacitors parallelly to a power supply, and if I want to have the same amount of energy with a single capacitor C equivalent, then C equivalent will be simply the summation of C1, C2, C3 plus and Cn. If you add the capacitances of all capacitors in the system, it will be equal to the C equivalent. Okay, so this is the discussion about the connections of the capacitors. Actually, I showed you parallel connection and serial connection, but in general we can have also mixed connections. I'll just mention about it, but I'll leave it to some solved examples when we review what we discussed so far. So just mention it. Mixed connection of the capacitors. So in the mixed connection you have both serial and parallel connected capacitors. For instance, if I give this, alright, this is C1, C2 and C3, and if I make a single capacitor system with the C equivalent, what is the C equivalent? Actually, you need to calculate the C equivalent part by part. How we can calculate? First, we need to calculate this parallel ones, and then move to this one. So if I call C equivalent part 1 of here, actually from the previous discussion we know it is simply will be equal C2 plus C3. So if I replace this C2 and C3 with the C equivalent 1, it is going to be the same. It is going to be the same system. Like this is C1 now, and now C equivalent 1 here, and they're going to be connected the same potential. And now we need to calculate the C equivalent of these two, but these two capacitors are serially connected, right? So C equivalent 1 over C equivalent in this case will be equal 1 over C1 plus 1 over C equivalent of the first part. Okay, this is just a quick generalization. In general, we usually have mixed connection of the capacitors, but actually the mix means the mixture of the parallel and serial connections. So you already know how to deal with. If you have mixed connection, then you need to calculate the C equivalents part by part. Okay. Now let's have a break here, and the next subjects will be the electric current. Okay guys, in this part we are going to start a discussion of the electric current. We define what it is and what it does in the electricity phenomena. Let's get back to our charge capacitor, and let me remind you what I told you before. If we have a charge plates and if we put them together, actually it forms a capacitor because it stores some energy, it has stored some energy. And when I connected this charge plates with a wire, let me just now give it a specific name, conductor wire, then the charges starts moving through this wire, and they go to the other plane, and this motion will last until all the plates becomes neutralized. All charges here, let's say delta Q is the whole charges accumulated on this plane, will start moving from this plate to the other one. So total charge moved will be delta Q to this plate, and then it's going to stop when two plates are neutralized. Now we discussed this side, right? Why they are moving, these charges are moving to the other plate, because since these plates are charged, it generates an electric potential difference between two plates, and this electric potential difference is associated with the non-zero electric field between the plates, and that electric field, remember from the definition, gives us some electric force on the charges, and this force starts moving the charges from one plate to another plate. And when all plates become neutralized, then the electric potential difference will be 0, electric field will be 0, so the electric force will be 0 on the charges, so charge motion will stop. Now, in this part we are going to focus on this semester. Actually, the electric current is something relevant to the motion of this electric charges. So let me just write the motion of the electric charges forms the electric current. So how we define the electric current? Let me just write it. The electric current is defined as the total electric charge passing through a material per unit time. So let's assume that the total charge will be delta Q passing through this conductor wire, right? Let's say the process will take time delta T. So the electric current I is defined the total charge passing through the conductor wire per unit time. So delta Q over delta T will give you the electric current over this wire. Before proceeding, let's just check its unit. What is the unit for the electric charge? The unit for electric current, we need to put the unit for electric charge, coulomb, and we use second for the time. So actually the unit of the electric current is coulomb per second, and we give it a special name after ampere. So we call the unit of electric current ampere. Okay, afterward we are going to use ampere as a unit of the electric current. But remember, the electrons, the protons are actually not too heavy. So when the electrons are moving from one plate to another one, actually they use quite fast. So actually the delta T is quite short when from here to here. The charges move quite fast, very close to the speed of light actually, quite fast. So actually delta T is almost 0. When you start measuring the time, you are not going to measure exactly 0, but delta T will be very small. So how we can define the current when delta T is so small? Let me just make some space. Okay, so delta T goes to 0. Actually, it's not exactly 0, but it's so small because charges are moving very fast. So we need to define the current at the limit at which delta T goes to 0, delta Q over delta T. What does it mean? Actually, this is nothing but the definition of the derivative of Q with respect to time. So if you know the total electric charge passing through a wire as a function of time, its time derivative, its derivative with respect to time will be equal to the current. And again, you can check the unit coulomb per second, and its unit will be ampere. Now, in this part, we are going to focus what is happening here. We already discussed this part, but now we are going to discuss what is happening when they are moving, when the charges are moving through a material, a conductor wire here. Okay. So let me draw the wire bigger. Okay, this is our wire, and these are our electrons are moving. Okay, and total charge is delta Q. And let's assume that actually, let me just define, this is the cross-sectional area we show it with A, and this is the length L, the length of the material. So let's assume that the electrons are passing through this wire with the velocity Vd. Okay, and if the total charge is delta Q, I can write delta Q in terms of the number of the electrons n times their charges. And remember, E is the smallest charge you can observe in nature, which is equal 1.602 times 10 to minus 19th coulomb. Alright, but let's assume that now delta Q is the number of charges per unit area. Okay, here the total charge passing through this unit area, unit volume is delta Q. Okay, so it's going to be n times n, and here the number of electrons per unit volume. So how we can define these two delta Q's? Delta Q will be equal total charge over volume, and volume of this material simply equal the cross-sectional area times its length. Or I can write delta Q will be equal the electric charge density times the volume of the material. Or let's keep writing, delta Q can be written by using this equation. It's going to be n times E times the volume. Okay. Now I'm going to move from here, but I need to make myself some space. Let's get back to our current equation. Okay, the current I is equal delta Q over delta T. Alright, delta Q can be written like delta Q times A times L over delta T. And delta Q, I can write delta Q in terms of the number of electrons. So I will be equal n times E, let me just write this way, n times E times the area L over delta T. Now let's take a look to this term. If the electrons are moving with the velocity Vd, let's assume that it is a constant velocity. So from the first semester, remember how we can calculate the path or the displacement in terms of the velocity and time. If Vd is constant, an electron comes from this point to this point at the time delta t, so L will be equal Vd times delta t, or Vd will be equal L over delta t. So this term is nothing but the velocity of the electrons, so I can write the current in terms of the number of them, their charges, the cross-sectional area times their velocity. Or I can reverse this relation. Their velocity can be written in terms of the current, n times E times the area. And this is called drift velocity of the charges. Okay, so we assume that the drift velocity is constant, and it is the velocity at which the electrons move through the material from one end to another one, and we assume it is constant, and we can calculate the drift velocity in terms of the current if you can measure number of the electrons, their charge, and the cross-sectional area of the material. So if we use a smaller area, then the drift velocity with the same current and same number of the electrons, the drift velocity will be faster. If we enlarge the area of the material, then they move slower, and the drift velocity will be less than this one. But the drift velocity actually is not the real velocity of the electrons when they are moving through the material. So how an electron moves through this material, let's take a close look to the material now. Now let me put my material here, the conductor wire. So And I'm going to discuss this over one electron. Let's assume that an electron just enters to the material at some velocity. It is going to be like, it doesn't have to be direct velocity. Now, before looking at the electron, let's see what is inside this material. Actually, this material is made of atoms. Atoms are including both electrons and protons, but in the free electron model, the electrons of the atoms are moving around. So we are going to have some positively charged ions everywhere in this material. Okay, these are positive ions. Okay, and this is the free electron model. Actually, it doesn't work all the time. It has some limits, but at the level of this course on Basic Physics 2, this free electron model should be enough. So let me just write free electron model. Now, what happens to this electron when it enters to the material? So it keeps moving, and then it's going to hit one positive ion. It's going to change the direction, and it hit another one. Change direction, hits another one. Hits another one. Hits another one. So it is going to move in this way. Let me just make a solid curve. And goes out of the material. So see, actually the path of the electron is not straight forward, and it is distracted by the positive ion. So actually it is, the drift velocity is just the average velocity of electron when it moves from this end to this end. Okay, but the real motion is more complicated than a straightforward path. And actually this behavior of the materials, these positive ions inside the materials, forms a resistance against the motion of the electrons. So the atomic structure of the conductor wire or conductor simply there forms a resistance against the motion of the electron here. So there is a resistance against the motion of the electron. Actually, the material doesn't like electron moving inside itself, so it keeps distracting it from its original path. So it gives us this complicated path rather than. But what happens if it has more ions inside it? So the electron will be distracted many more times than usual. Okay. So the resistance will be larger, will be greater. If it has less positive ions, then the electron will be distracted less, so the resistance will be less in compared to the case of more positrons. So how we can formalize it, how we can measure it, or present it in some equations. So let us have a wire here. Okay. Now, in this case, there is no charge moving inside it because I didn't apply any electric potential difference, right? This is a conductor wire, remember, and inside it the electric field is zero. Remember from our previous discussions, and even though electric field is zero, still there is non-zero electric potential, but that electric potential is constant everywhere inside this conductor. It means there is no electric potential difference between this end and this end. So in this case, zero electric potential difference means zero electric field, and zero electric field means zero electric force. And so the electrons inside this material is not being forced to move. But when I connect it to a circuit, to a power supply, V, that power supply with the electric potential V generates an electric potential difference between these two ends as much as V. That potential difference will generate an electric field, let's say in this direction, and then the electrons start moving from this end to this end. Remember, the motion of the electrons are in the opposite direction of the electric field, but we are going to assume the electric current will be in this direction. So when we connect it to a power supply, we are going to observe some electric current through this material. So I'm going to call it I1. Okay. And we know this I1 is somehow, related to the motion of the electrons. But let's see what may happen when I replace this material with another one. So this is another one. Their shape will be identical, same length, same area, but different material. So I'm going to connect it to the same power supply, V, and again it's going to be an electric field, the same electric field because same potential, and the electrons starts moving from here. But as I said, these two materials will have different atomic structure, so the path of the electrons will be different in two cases. So when I connect this material to the power supply, I'm going to observe another current, I2, in this direction. And these two currents in general are not equal to each other. Now, if I define a linear relation between electric potential difference and I1 and between the same electric potential difference and I2. So there should be we can define a linear relation between the electric potential and the electric current, but when I change the materials, I am seeing different currents corresponding to the same electric potential. So I can put some proportionality constant, R1 and R2. That R1 and R2 differ from one material to another material. So we call this the resistance of the material. This R1 is the resistance of the first material, and this R2 will be the resistance of the second material. Okay, so then we can measure the resistance of the material by applying some electric potential difference and measuring the current we obtain. And with different materials, we are going to obtain different currents, and the relation between the electric potential and currents are provided by the resistance of the material. So we can define a linear relation between the electric potential and the current through the material, electric current, as V is equal R times I. V is the electric potential we are applying to the wire. I is the electric current we measure over the wire, and this is called resistance. Okay, and this relation is called Ohm's law. All right. Okay, so this is defined. This is Ohm's law. According to Ohm's law, there is a linear relation between the electric potential and the electric current through the wire, and this relation is formed by the resistance of the wire. So this resistance is depending on the atomic structure and also the geometry of the material, and see how it is depending. Okay, let's have this wire again. So the current I is passing through all. So in the unit area, unit length, let's assume that J, here J is the electric current in the unit area, just like this. This is, let's say, unit area, okay? In the unit area. And when we apply a potential difference between two ends of this wire, the electrons will start moving, so we are going to observe the electric current, and I define J, the electric current, as the electric current density, means, in other words, the electric current in the unit area. So J will be equal I, the current over the area, the cross-sectional area. Okay, and we call it electric current density. Let's say L is the length, so that potential difference will generate an electric field here. An electric field can be written V over L. Remember, we calculated all of this. Actually, the electric potential is equal E times L, or D that time we used. So we can write electric potential is equal V over L. So let's get back to the Ohm's law. Okay, V is equal the resistance of I. This is the resistance of the material, and you don't have to memorize it because it is unique to each material. If you have different materials, you will have different resistance. You don't have to memorize. I'm going to provide the resistance of the different types of material when you need it in the exams and homework problems. From here, I can write the resistance in terms of V over the electric current. So let's play with all of this and plug them into this equation. So R will be equal E times L for the electric potential over the electric current density times area. Okay, I'm using this one. And from here I can write E over J, and I'm going to put rho here. Rho measures the conductivity of, resistivity of the material. So, resistivity of material you can write by comparing these two equations. E over the electric field over the electric current density, and rho is defined as the resistivity of the material, and from this equation rho will be equal the resistance, the resistance of the okay, not this one, sorry. Okay, I can write like E over J times L over A. This E and J, E is the electric field, J is the electric current density, and again, applying an electric field gives you different electric current density depending on the material, and we call this the resistivity of the material. Okay, so let me make myself some space. Following the last equation, so we can write the resistance of a wire or conductor can be written E over J times L over A, and this E over J is the resistivity of the material. Okay, we show it with rho equal E over J, called resistivity. So the resistance of a material can be written in terms of the resistivity times its length and its cross-sectional area. Okay, so let me clean up this bottom side and let's discuss what this equation means. Okay, this rho, the resistivity of the material, is relevant to the atomic structure of the conductor wire. So this is coming from some inertial property of the materials, but L over A is defining the geometry of the wire, right? If I draw the wire again, so this is the cross-sectional area, this is length L, and rho is somehow related to the positive ions inside it. We cannot change the rho, right? Rho is unique to the material, but we can play with the geometry. We can change the area, we can change the length. So rho is here, but if you have a longer wire, it means the resistance will be greater, because resistance is directly proportional to the length of the wire. If you enlarge the area, cross-sectional area of this wire, the resistance will be reduced, right? With a larger, a thick wire, you may have a less resistance. Or if you just shrink if you shrink the area, if make it like less thick, then A will be smaller, R will be large. So actually, the small area will give you a great resistance. Okay, so resistance here is resistance of a material against the motion of electron is relevant to its atomic structure encoded in rho and its geometry, length over A. Okay. So what we can do with the resistors, actually we can play with the resistance, and we will show a resistance in a circuit with this notation. So this will show you resistance. And then when I connect it to a power supply, then the charges will start moving. Let's say now the current in terms of electric current, and it passes through this material, comes back to the electric the power supply. So when it is passing through a resistance or a resistor, we can also call it like resistor. Okay, resistor, actually we can feel something. If you put a bulb, light bulb for it, for instance, let's say this is a light bulb, and this is the resistors inside it. And if it is in the, when the current is passing through this light bulb, you are going to see some lights around it, right? Or if you put a heater here, okay, then if it is a heater, so you will feel some heat around it. Actually, when the current is passing through this resistor, this resistor is going to absorb some energy of the electrons, moving charges, and it's going to give that energy, convert to that energy depending on what you are using. If you use a light bulb, you are going to see some lights actually giving around. Actually, this is how we are enlightening our rooms, our houses. And if you put a heater as a resistor here, so when the current is passing through, you will feel some heat. Actually, you can heat up anything. Actually, their basic mechanisms is like here. So there are something actually we can use this resistors actually in our daily life to obtain some benefits like lights, heatings, or something else. Also, your phone is full of resistors. So actually, these resistors are converting the energy that, so in a way, you can use your phone. And similarly, if we have more things, actually, what if you have both? If you want to enlight your house and also heat up your house? It means what if you use both two or more resistance and connect them? Again, the connections will be two different ways. How to connect? Actually, we discussed them when we discussed the capacitors, but we are going to follow the same discussions, but we are going to have some different results because now we are dealing with the resistors. If you have two resistors, you can connect them in two ways. One is the serial connection. And in serial connection, actually, you can connect this way, connect two resistors in this way. And this is our power supply. Let's call it R1, R2, and the current, see the same current is passing through all the resistors and comes back to the power supply. So in this case, as we discussed in the case of the capacitors, it's going to be, there will be a potential difference between the ends of R1, which is going to be called V1, and also some electric potentials between the ends of R2. We are going to denote it with V2, and in this case, actually V, the electric potential of the power supply should be equal V1 plus V2. But by using Ohm's law also, we can write V1 will be equal I times R1, right? The same current is passing through, so I'm not using I1 or I2. And V2 will be equal I times R2. We can write it and we can put it here. But what about V? Now again, you have two resistors actually giving you some energy, but you want to have the same energy, but by only using one single resistor. So you want to use a single resistor, but you want to have the same job actually. You want to have the same energy from R1 and R2 with only a single one. So if I put this, if I form this system, this circuit, the same current will pass through this single resistor, but you are going to have the same energy. So assume that you know R1 and R2, but what is R equivalent? We are going to call it equivalent resistance or R equivalent in short. So you want to have this circuit instead of this one, but you want to have the same energy. So how much resistance you need to use in this system? Let me just rewrite this. I'm going to draw them again, but smaller. So this is your first circuit, like R1, R2 and V, and this is V1, V2, and the same current is passing through all resistors. But you want to have this circuit are equivalent, same power supply and same current. And from here, V1 is equal, by using Ohm's law, I times R1, V2 is equal I times R2, and from here also V is equal I times R equivalent. Now, we know from this circuit, we know V is equal V1 plus V2, okay? So we are going to use this equation to calculate the R equivalent in terms of R1 and R2. So I'm going to write this one. V is equal I times R equivalent equal V1 is equal here I times R1, and V2 from here I times R2. So let me rewrite again by using a common parenthesis of the electric current R1 plus R2. So if I cancel these two I's, electric currents from both sides, R equivalent will be equal R1 plus R2. So actually you can either use this one or this one. Actually both systems will make the same work, will give you the same energy or same job they are going to do. But if you don't have two resistors, or if you want to use only a single resistor, then you need to use a resistance which is simply the summation of two resistors here in the case of serial connection. So let me summarize and generalize it. In the serial connection, you may have as many resistors as you want, right? So connect to the same power supply. Let's call it R1, R2, R3, Rn. But if you want to form this circuit with only a single resistors, which is going to do the same job, I mean V, current I, the same current and same power supply. So in serial connection, you can write the R equivalent is simply summation of the whole resistance connect to your original circuit. So R1, R2 plus R3, Rn. So this is the generalization if you have more resistors than 2, 3 or 4. Okay, so this is one way you can connect your resistor serial, let's say like your light, your heater, your phone, your some other things, your robot and some other things. So you can connect them in serially to each other. So you can serially in that way or if you want to have only a single one making the same job, so with the R equivalent, you can calculate R equivalent in the serial connection simply as a summation of the whole resistance in your original system. The second way to connect this resistance is the parallel connection. Alright, so now parallel connection of the resistance, parallel connection of resistors. And now you are familiar with the parallel connections. Now at this time we are going to use resistance instead of capacitors. So if you have two resistors, and if you in the parallel connection you connect them as you see from the figure. So this is the power supply, and this is R1, this is R2. Now the electric current I is going, but at this point there are two ways the electric current should go. So the electric current will split, so I2 will follow this way, while I1 will follow this way. Where in the parallel connection, see the electric potential between the ends of R1 and between the ends of R2 will be the same. So actually VR1 will be equal, VR2 will be equal V itself. On the other hand, the currents are now different, but the electric charge conservation, here I is coming, electric charge conservation requires I is equal I1 plus I2. Okay, you wanna construct a simpler circuit with only a single resistance. So I'm going to call it R equivalent, the same electric potential and same current. So what is R equivalent? Now let's first write, we are going to use this equation, but by using Ohm's law, from here I1 will be equal, by using from the first one, V over R1, right? And I2 from the second resistors by using Ohm's law will be V over R2, and from this system the I will be equal V over R equivalent. So now we are going to use this equation here. So I plugging this will be equal V over R equivalent will be equal I1, which is simply equal V over R1 plus I2 by using this equation V over R2. If I cancel all electric potential from the all terms, then in parallel connection we can find the R equivalent as the summation of the inverses of 1 over R1 and 1 over R2. So in the case of parallel connection, you can calculate the inverse of the equivalent resistance as a summation of the inverse of R1 and inverse of R2. So let's summarize and generalize. If you have n resistors in the parallel connection, like this is R1, this is just R2, R3, Rn, so R1, R2, R3, Rn, and they are connected to the power supply V. In the parallel connection, each will have, total current will be I, but each will have different current, right? Because the current will split at the junctions here. So I3, In, but the total current, will be equal like I1 plus I2 plus I3, In should be equal to the total current here because of the electric charge conservation. And if you want to install a simpler circuit with a single resistance R equivalent with the same power supply and the same current, then you can calculate the R equivalent, but inverse of R equivalent in the case of parallel connection will be simply equal 1 over R1 plus 1 over R2 plus 1 over R3. Okay, and this is the equivalent resistance, how to calculate the equivalent resistance in the case of parallel connection. Alright, now, actually, unofficially, we introduced to you some electric circuits, including resistance here, but before also we considered some electric circuits, which were including the capacitors. Now, we are going to stop here for 5 or 10 minutes, then we are going to continue to analyze the electric circuits. So let's have a 5 minutes break and continue after that. Okay guys, in this third and last part of this video, we are going to discuss the electric circuits and Kirchoff's rules. Actually, we already took a step into the circuits when we were discussing the connections of the capacitors and the resistors. Now, to the electric circuits, let me just define you roughly. The electric circuits are some setups in which we connect the capacitors and the resistors, and we take some benefits, or we can have some benefits from the capacitors and the resistors. What kind of benefits we can have? For instance, when we discussed the capacitors, I told you that the capacitors can store some energy, electric energy inside themselves. So electric circuits may make possible to use that energy for some use. For instance, like we can connect the capacitors to our phone to use it to use the energy stored in the capacitors. Also, we discussed the resistors. Actually, resistors are like almost everything. The light bulbs are basically are resistors, or heaters are actually resistors. So we can use the resistors by eating up the energy and converting it to a light or heat or something else. So now after we introduce the electric circuits, we are going to classify the capacitors and the resistors like the electric circuit elements. Okay, so if I write the electric circuits elements, we mean the capacitors and resistors. Actually, they have their own different use. And we already mentioned about this, the energy storage and converting the energy to something useful, like heating or enlightening, so on. Actually, these are not the all circuit elements, but so far we discussed the capacitors and resistors, so for now we are going to stick with these two circuit elements and we are going to use it. But before using it, let's take a close look how they behave when they connect to circuits. Okay, so first I'm going to start with the capacitors. Okay, if this capacitor, okay, let's say we have a resistor and then also a power supply like this. CR, let me put a switch here. I'm going to give you a better circuit. So if we connect the capacitor here with, let's keep a resistor in the circuit. This is resistor, this is capacitance, and this is power supply. So if we have a capacitor in the circuit, how this capacitor behaves. First, we need to know if this capacitor is empty or full when it is connected to the circuit. So actually, we need to turn on the switch. So if a capacitor in an electric circuit, it behaves like a resistor, but not resistor, and it consumes energy until it is fully charged. Okay, if the capacitor is empty when we connect it to the circuits, actually it behaves like some circuits elements eating up some energy and storing it in itself until it becomes fully charged. When it becomes fully charged, when it becomes fully charged, then it starts feeding the circuit with some currents. What it means, for instance, I mean, if when I connect an empty capacitor into the circuits with a resistance, actually it doesn't give anything to resistor because it is empty, it has nothing to give. But after some time it's going to be fully charged. So for instance, if I turn off this switch, so actually I disconnect the power supply, but since this capacitor is now fully charged, it starts feeding the circuits with a current, and it runs the current over the R, so you can still have some use of the resistance. What kind of example I can give? For instance, this is the battery of your phone, and this resistance is your phone, and this is the power supply. So when the battery of your phone is empty, you plug it you plug it to the switch, so you have a power supply, so it starts running your phone. Actually it is like here, you start running your phone, but meanwhile you are also charging the battery of your phone. But when it gets full, the battery of your phone gets full, then you can plug it off, so disconnect the power supply, then still you can use your phone because the battery of your phone is now feeding the system, feeding the circuit. So this is the behavior of the capacitance, and actually I didn't mention separately, but I mean still now we also discussed about the behavior of the R, the resistance. Resistance always eats up some energy, like your phone, okay? Your phone never gives you some energy, it always eats up to give you some use, some benefits, okay? So the capacitance behaves like this. When it is empty, it behaves like some circuits elements eating up some energy and storing it. When it is full, so it behaves like a power supply, a second power supply when it is full, so it feeds the circuit with some currents, okay? And resistance always eats up energy, okay? Eats up some energy and convert it to the lighting or heating or some complicated types of energies which is used in your phone here. So I usually talk about the energy, so how much energy actually we can store in a capacitance and how much energy we can obtain from a resistor. Actually we already discussed the energy stored in a capacitor. Actually we calculated it in the last video, or maybe the one before the last. So the energy delta U for the capacitor, we calculate is 1/2 Q, the total charge accumulated in a capacitor, times V. Or by using the definition of the capacitance C times V, we can calculate delta U will be equal 1/2 the capacitance times V squared. Let's play it a little bit more. What is V? By using the electric field, simply it is like E times D. D is the separation between the plates. And if I write it here, delta U, then I will have delta U will be equal 1/2 C times E D squared. Let's also remember what the capacitance of this plate is. Simply it's going to be epsilon 0 A over D. So if I plug it here, the total energy stored in a capacitor also can be written in terms of the area, separation, and the electric fields. It's going to be 1/2 epsilon 0 A over D times E times D squared. Let's keep playing with this equation a little bit more. I'm going to continue from the top. If I simplify this equation, delta U will be equal 1/2 epsilon 0. We will have A electric fields times D. All right, so this is the actually also the energy written in terms of the volume of the capacitor. So I can write epsilon 1/2 epsilon 0 the electric fields times volume. All right, volume here is equal A times D. So this is the energy stored in a capacitance, the total energy. But if I define the energy density per volume, per unit volume, I need to, if I show it with U, it is delta U over volume. So if I divide this equation with the volume, I'm going to have 1/2, it's going to be E squared, 1/2 epsilon 0 and electric field squared will give you the energy density in a capacitor per unit volume. All right, so this is just a reminder and playing with the energy stored in a capacitor. So we can also define the energy density in a capacitor in terms of the electric field. Actually, this is only electric field here in definition and in calculation of the electric energy density. This is constant epsilon 0, we already know it, and 1/2. So we can write the energy density in terms of the electric with square of the electric field, and multiplying this energy density with volume simply gives you the total energy stored in the capacitance. So what about the energy we can have from a resistor? Okay, so now let me just change the title. Energy out of a resistor. Okay, now we have a resistor now. Here, this is R, a current I is going, and this is connected to a power supply V. So we know the energy. Now some charge, let's say dq charge, is moving from the power supply and passing through the resistor and comes back to the power supply. So how much energy you need to have to move this dq charge from positive side to the negative side? So du will be equal, simply remember, V times the charge. Remember, when we defined the electric potential, we defined it in terms of the electric potential energy, and when we multiply the electric potential with the charge, it will give us the electric potential energy. This is from the definition. But if we can also define dq, the current here is equal dq over dt. From here we can write dq will be equal the current times dt. If I plug it into this equation, du will be equal V times I, the current, times dt. If I integrated it over time, the right hand side over time, then the energy out of a resistor will be the electric potential V times the current passing through the resistance times T. We can also call it delta T. All right. So actually a resistor eats up more energy as time passes. Okay. If you use the heater for 1 minute, you will have some heating energy. If you use your heater longer than 1 minute, you will have more energy, because the energy out of the resistor is proportional to the time you are using it. We can also write the energy out of the resistors in different forms. Just let me give it to you. So energy delta U out of the resistance, we find the electric potential, electric currents times delta T. But by using Ohm's law, which is equal I times the resistance, the Ohm's law, we can also, if I plug Ohm's law into the energy equation, I can write delta U will be I squared R times delta T. So you can also calculate the same energy, electric energy out of the resistors in terms of the current, square of the current, resistance, and the time. So this is the energy you can have. Actually, if you put a light bulb, so this much energy will be converted to light. If you put a heater into the circuit, so this much energy will be converted to heating energy. But if I define the power is the energy released, let's say released for here, released per unit time. So power actually will be equal delta U over delta T, and by using this equation, the power from a resistance, the power of a resistance can be calculated as like I squared R, or getting back to the electric potential by using Ohm's law, it's going to be electric potential times current. So you already know what power is, but this is just refreshment, and also apply it to the electric circuit. So actually this much of energy for resistors, I squared times the resistance times delta T, will be run in the circuits. If you have a capacitor, you are going to have 1/2 C and V squared energy stored in the capacitors. So in this video we discussed the connection of the capacitors and the electric resistors. So now what if we have circuits, a mixed circuits or connection, like here, let's say we have a circuits with a resistor, with a capacitance, and here V. So the current goes like this. This is C and this is V. Now, actually, with this circuit, I'm going to introduce you the Kirchoff's laws. The Kirchoff had two laws. One is the loop law. This is a loop, right? This circuit is simply a loop, and we can move. The current is moved within a loop. The Kirchoff's first law, which is called Kirchoff's loop law, says that the total energy within a loop should be zero. Actually, this is coming from the conserved forces. Remember, electric force is a conserved force. So you are starting here for a charge, is moving, charging the capacitor, and then passing through a resistor and comes back to the same point. So actually you are starting from a point and coming back to the same point under a conserved force, which is electric force. So actually the total energy difference should be zero, right? Because the total work done by the electric force will be zero. But how we can see it? Now, if you follow the path of the current in the same direction, actually you can follow the other direction, but here I'm going to follow the same direction with the current. So first we are passing a power supply, right? In this direction. So this is minus, this is positive, this is, see, let's say, if we follow the same direction of the electrons, actually this contributes, this power supply contributes the energy of the circuits, right? So it's going to be plus V. That V, actually, if we charge with the Q, it gives you something energy, in dimension of energy. So it is going to be V. So let's keep going. Then we come to the capacitor C. So this is going to be plus, and this is gonna be like negative and plus. So if we move like this in the same direction again with the current, it's going to be plus Vc. Vc is the electric potential between the plates, and what is Vc? It is simply Q over the capacitance. Now we are now coming to the resistor. Okay, we come to the resistor. So the current is going in this direction, and this is resistor. If we move in the same direction, but the behavior of the resistance differs itself from the other elements of the circuits. So even though we are moving in the same direction with R, it's going to be minus VR. Why minus? Because this resistor is not contributing to the energy of the circuit. It is taking some energy for itself. It is consuming the energy. That consumption is coded with the negative sign. And Kirchoff loop laws, let me clean up this part. Kirchoff loop law says that the total energy should be zero through the loop. So V here plus Vc minus VR should be equal 0. What is VR? The current times R. Alright, so if we plug these equations, let me now clean this up. So V is provided by the power supply, plus for Vc I can write Q over C, and Q is I times T, the current times time, and minus I times R will be equal 0. Okay. And this is the I over C also, again, if we just take the energies. Alright, so this is Kirchoff's loop law. What if we have multiple loops in the system? Kirchoff says that moving a charge through each loop should be 0. So if we have multiple loops, like this, for instance, let's say we have R, capacitor, another R, another capacitor here, and another capacitor here, and a power supply here. Let's say this is R1, R2, C1, C2, and C3. So this is V, and our charge is moving from here to here. Let's call it, we have now two loops, right? Here and here. So first of all, let's choose, this is I, the total charge leaving the power supply. Let's assume that total I1 is moving through here, and I2 moving through the second loop. So Kirchoff loop law says that each loop, while we are moving each loop, we should have 0. So let's say this is first loop, and let's say this is second loop. Okay, for first loop, Kirchoff's loop law says that now we are going to move again. We have a power supply V. We are moving through the same direction with the current. So I is, let's say I is moving over C3 plus Q over C3, okay? And then we come to R2, but be careful, I assign I1 for R2. So R1 is moving minus I1 times R2, and nothing else. We come back to the source, it should be equal 0. And from the second loop, now we are going to move over here. Now we need to check what we have. If we start here, we are moving in this direction, but I1 is moving in this direction. So we are in the opposite direction of I1. So minus I1 times R2, and Now moving with the same direction with I2 plus Q, let's call it like Q3 here, Q1 over C2. Now we come to another resistors and we are in the same direction as the current passing through it. So minus I2 R2. Let's keep going. Now we come to this one. This is Q2 plus, and we are in the same direction as the current. So Q1 over C1, and it should be equal 0 as well. Okay, this is like the loop law of Kirchoff's. Actually, this is just the general explanation of the Kirchoff's laws. We are going to have some solved examples to clarify it in another video, not here. So first here, I'm just introducing you to Kirchoff's laws, and the first one is the loop law. It says, let me just repeat, if you move a charge through a closed loop from here to here, then the total energy should be equal 0. Why? Because our charge starts from here and coming back to the same point, and we know the electric force is a conserved force, so if it comes to the same points, its work will be 0. 0 work doesn't contribute to the energy of the system, so the energy difference will be equal 0, and it is true when if we have multiple loops, so we just repeat the same law to each loop one by one. So for the first loop, I can write this equation. For the second loop, I can write this equation, and each should be equal 0. By solving all these equations together, then we can calculate what is Q1, Q2, Q3, I1, I2, and so on. Also, we can calculate V. We are going to apply these laws when we have some solved examples, but not in this video. Okay, so the second law of Kirchoff's is called junction law. So Kirchoff's junction law. Actually, we see it before without using a name, but let me first show you what a junction is. So if we have a circuit like this, let's say if you have a circle like this, let's say this is the power supply, R's, you can call R1, R2, R3, C1 and C2. Now the current current starts from the power supply and it comes to that point. That point actually is a point at which the current should split, right? Some current, let's call it I2, I is coming here, I2 following this way, I1 following that way, but we have another point, so I1 comes to that point, but it has to split in two ways. Let's call it like I3 and I4. Alright, so there I4 is moving here and coming to here, and there is another point at which I2, I4 and I3 meets again and gives you what? Should give you I1, right? Because of the electric charge conservation. But I1 comes back to this point and it meets with I2, so the total charge, total current I should come back to the power supply. So in this circuit we saw some points at which the current gets split. So these points, like here, here, here and here, these points are called junctions. Okay, at a junction, when a current comes to a junction, it has to split in the ways. So here, like we have two ways, but we may have 3, 4 or more ways as well. So at a junction, it's defined like the point in the circuits at which the current should split into different ways. So what it says, the Kirchoff's junction law says total electric current at a junction is equal to 0. What I mean, let's say this is a junction, so let's say I1 is coming, I2 is coming, but I3 is going away, I4 is going away, I5 is going away. This is a junction. It says if I sum up all these currents, it has to be equal 0, but how? So we are going to assign some signs, like positive signs for the currents coming to the junction and negative signs for the currents which are going away from the junction. So according to the junction law, we can write like I1 is coming plus I2 is coming to the junction, but I3 is going away, minus I3, I4 is going away, minus I4, and I5 is going away, so minus I5 should be equal 0. Or we can write I1 plus I2 should be equal I3 plus I4 plus I5. And actually we used it a lot without naming it, without putting it as a subject of a law, because it arises this from the conservation of the electric charge. Alright, so these are Kirchoff's laws. We have two laws. One is for loops. So Kirchoff law says that like the total energy or total electric potential, if we write the energy in terms of the electric potential, through a loop should be equal 0. And if your circuit have multiple loops, 2 loops, 3 loops, or 4 loops, each loop should give you a 0 for the total electric potential difference. And the second law is about the junction in a circuit. And Kirchoff's junction law says total electric current at a junction should be equal to 0. So this is a picturizing what it says. We have some currents coming to the junction, and we have some other currents going away from the junction. And if I add them up by keeping the signs positive and negative, positive for the currents coming to the junction and negatives for the currents going away from the junction, so it has to be equal 0. Or I can rewrite it in another way. I1 plus I2, all incoming currents should be equal I3, I4 and I5, all outgoing currents. And actually this is nothing but the conservation of the electric charge. Okay, we are going to stop here for this video. So we defined the circuits elements like capacitance and the resistors. Actually we can have more circuits elements, but so far we covered the discussion for the capacitance and resistor, so we keep them. Maybe later we can add a third circuit elements, but it is too early for now. Next video, actually we are going to stop here for now, and next video we'll be reviewing what we discussed so far. We are going to review the subjects we discussed over some solved examples. So next video will be just a recitation and application of what we learned. So we are going to cover all the subjects we covered so far, and then we can continue with new subjects. So that's all for this video. Hope you enjoy it.